All right, we're going to take a look at a few additional problems that seem to give people a little bit of trouble. First off, up here I've got a piecewise function, but the piecewise function involves one of our library functions, the absolute value, as well as the transformation piece. Now, if we can remember that kind of stuff, it makes the graphing easier. However, anytime we forget which way these transformations are moving, or if we forgot what the absolute value looked like, then start plotting points. We can plot points and come up with the graph. But let's take a look at this. So, absolute value of x minus 1. That is a v-shaped function shifted to the right 1 unit. Right? So if I'm shifted to the right 1 unit, my vertex is going to be right there at 1, 0. I'm going to have this V shape coming through here. Now, how wide the V needs to be, where it ends, I'm given a domain restriction over here of 0 to 4. So I'm going to use those endpoints. If I substitute 0 in, 0 minus 1 is negative 1. So absolute value of negative 1 is 1. And that's going to give me an open circle there at 0 on open circle because I don't have the equal to. If I go to the right at 4, let's see, we'll go 2, 3, 4. If I put 4 in, 4 minus 1 is 3. Absolute value of 4 is 3. So I've got the point 4, 3 right here, and that one's a solid dot because I do have the equal to. And here comes that first part of the piecewise function, okay, between that 0 and 4. Now let's look at the second part. Absolute value of x plus 1. Well, still I've got that V shape. The plus 1 is shifting it left. So that's going to move my vertex to right here at negative 1. Okay. Now let's check our endpoints. At negative 4, negative 4 plus 1 is negative 3. Absolute value of negative 4, absolute value of negative 3 would be 3. So I'm over here at negative 4, 3. Slide that down just a little bit there. Okay. There's that first part. And if I put 0 in, I get 1. And again, I'm going right to that open circle. And it doesn't close the circle because it still just has the less than. So let's see here. That's negative 1. That's negative 4. 1, 4. And that's up there at 3. And that open circle is at 1. The other thing we're often asked for on something like this is a domain and a range. Okay? We can tell the domain from this setup right here. Okay. However, I think a lot of times it might be easier to tell what the domain is by looking at the sketch. So if I do the sketch first, then I can move left to right and take a look at my domain. So the domain. We are left to right. We're going to start at negative 4, x value is at negative 4, and go all the way to 4, except we're leaving out the 0 because I've got that open circle there. The way I can write that is negative 4 to 0, parenthesis on the 0 because I'm not including it, bracket on the negative 4, union 0 to 4, and again, parenthesis on that 0, bracket on that positive 4, and that gives me that domain value. You could write it out in words and say all x values between negative 4 and 4, excluding 0. We've got to make sure we've got 0 left out. Range. Definitely need to look at my graph. Very tough to tell range looking at an original setup, but I can look at the graph. Lowest number to highest number. Well, the lowest y value would be 0 because it comes down to the x-axis. So I'm going to have 0, comma. Highest y value is 3. Both endpoints were at 3. If one was higher than the other, I need to look at the highest one. They happen to be the same. So 3 would be that end for the range, and we're including it. The question still sometimes comes in at the 0. Well, I guess at the 1. X is 0, y is 1. Hey, there's a circle. Yeah, but I covered it over here. So I did hit that y value of 1 in 2 different spots. So that gives me my domain and range along with my graph. The next type we want to take a look at from earlier in the course is classifying or determining if a function is considered to be an even function, an odd function, or neither. Even meant it had y-axis symmetry, odd was origin symmetry, and neither didn't have y-axis or origin symmetry. Well, very tough to tell if I don't have a picture of the graph to kind of see if it does have a y-axis symmetry and origin symmetry or neither one. So, investigating here, what we want to take a look at is what happens if we find f of negative x. I've got 3 different functions we're going to look at here. I'm going to find f of negative x. So if I substitute negative x in for x, this would be 4 absolute value of negative x plus 3. So simplified down, the absolute value of negative x is the same as the absolute value of x, because the negative's not going to matter. So this would be that simplified function. Even means I get the same function I started with. Odd, the negative of the function I started with. Neither, I don't get either one of them. So on this one, I got the exact same function I started with. Even. Second one, I'm going to find that f of negative x first. So I'd have 2 times negative x times negative x minus 1 squared. So, kind of a little bit more of a pain to simplify on this guy. First off, 2 times negative x is negative 2x. Kind of that easy part. It's that square that I'm looking at as far as what's going to happen here. So the question is going to become, I know this is the negative. What's happening with this guy and this guy? Did that negative x change a lot of things going on? Well, let's take a look here. Sometimes it would be helpful to multiply things out. So I'm going to go right here at the bottom. If I had x minus 1 squared, if I multiply this out, that's x minus 1 times x minus 1, which would be x squared minus 2x plus 1. That's what the original one had in that spot. If I go the other route, negative x minus 1 squared. Right? Negative x minus 1 times negative x minus 1, x squared. Then that would be plus x, and plus x is plus 2x. And then plus 1. Right. That's what I'm looking at on that part. So what that's telling me is, right here, x squared plus 2x plus 1 for that. It's like, all right, is this going to be the same as this one? Again, if it's helpful, you can kind of squeeze right in here. This would be 2x times x squared minus 2x plus 1. I've got some differences in some signs there for sure. So it's not the same, which means it's not even. Okay. Well, let's check the odd. Okay. Odd would be the negative of the original. Very tough to tell when you've got something not multiplied out sometimes. So let's take a look at this. Okay. I am going to just distribute this. Okay. And I'll just put it right here. This would be 2x cubed minus 4x, and we'll come back to that problem. 2x cubed minus 4x plus 2x. That's that one multiplied out. This one multiplied out, negative 2x cubed minus 4x minus 2x. So the negative and a positive is negative, and then that negative. And then I can kind of investigate a little bit there. X plus x is 2x plus 1. All right. And I'm trying to decide, all right, even, odd, or neither. All right, we already know it's not even, so it's not the same thing. Odd would be, what if you multiplied the original by a negative 1? So if I multiplied this one by a negative 1, I would have a negative, a positive, a negative, and that would not be that one. Okay. So odd would be the negative of the original. This is forcing this guy to a neither. It's not the same as the original. Or excuse me, not the negative of the original. Same would be the even. It's not the negative. Again, if it was the negative, all signs would change, and they didn't all change. These guys in the middle stayed the same. Sometimes if I saw something like this originally, it could be very helpful to just go ahead and multiply it all the way out and then investigate from there. Because then it would look like this guy right here. Right? Went through there. It would look a little bit more like that. Except, you know what, I made a mistake there. I had my square. When I multiply that out, it would help if I multiply that out if I did it correctly. Square. I had to have a square sitting there. Forgot my square because x times x is x squared. It's not changing the fact that it was still going to be a neither though, because those two signs didn't change, the others did. Doesn't affect that. Third one over there. Space here. I find f of negative x. 7, negative x cubed, 5, negative x, minus 8. If I cube a negative, that gives me a negative. So this will be negative 7x cubed, minus 5x, minus 8. It's like, all right, was this the exact same? No, it's not. Not the exact same, so it's not even. Odd. Is this the negative of the original? Again, think of it as, if I were to distribute a negative through here, would I get this? Well, that would become negative 7x cubed, negative 5x, plus 8. Whoa. I'm not getting the negative of the original, so again, neither. I didn't have an odd one up here. Let's throw an odd one up here so we can just make sure we have that. Let's go f of x equals 4 x to the 5th plus 7x cubed minus 2x. We'll do something like that. F of negative x. 4 times negative x to the 5th plus 7 times negative x cubed minus 2 times negative x. So a fifth power on a negative becomes a negative, so negative 4x to the 5th. Third power on a negative is negative 7x cubed. And negative 2 times negative x is positive 2x. This one would be odd. Obviously not the same, as exact same as the original, so evens out. Now I'll look at it as, if I were to multiply this by a negative, that would become negative, that would become negative, that would become positive. Hey, I got odd, all of them changed. It is the negative of the original. All right, now, later in the course, another one that gives us a little bit of a fit is regarding a hyperbola. Now, similar to ellipses or parabolas, oftentimes we get a general form and we have to complete the square to get them into our standard form so I can tell what the different pieces of the hyperbola are as far as center, graphing it, asymptotes, all that kind of stuff, transverse axis. So if I'm given a general form, I want it in standard form. Oftentimes, when we write a general form, we always have x first. But I need to remember that in a hyperbola, it's the square, the first one squared minus the second one squared. If x was first, or y could be first. So in this case, I want to rewrite this as 4y squared minus 16y minus x squared minus 2x equals negative 11. So for me to get that standard form, I'm going to have to complete the square with the x's and y's. So I need to get those x's together, y's together. I move the 11 out of my way to the other side. And the reason I put the y's first, it's the positive one I was looking for there. Okay. So to complete the square, next thing is my leading coefficient's got to be a 1, positive 1. So I'm going to factor out the 4. So I have 4 times y squared minus 4y. And then on the x's, I need that positive 1. I'm going to factor out the negative 1. So then I'd have x squared plus 2x, because I factored out the negative, and then still negative 11 there. Let's get the square completed. Y squared minus 4y. All right, half of 4 is 2. Squared is 4. I've got to balance this on the right side, and I'm going to add 16. I'm adding 16 because inside I added 4, so really on the left I added 4 times 4, which is my 16 there. Minus 1. I don't really need the 1 there, but sometimes it's helpful to see it there. X squared plus 2x, half of 2 is 1, squared is 1. And to balance it, I'm adding a 1 inside, but overall I'm subtracting a 1. So if that negative 1 was redistributed, I'm really subtracting a 1. So now we've got 4y minus 2 squared minus 1x plus 1 squared equals 4. We're getting close to that standard form. I need to divide the 4 over. So y minus 2 squared. 4's cancel, but a lot of times in the standard form it might be more helpful to kind of see that 1 down there. Minus x plus 1 squared over 4 equals 1. There's my standard form. There's where what I can use to find all of the different parts. Okay? So I need that piece. Okay? This is telling me that y is first. That means the transverse axis is going to be the y-axis, since that's the one that's first. My center is always that HK. In this case, it would be negative 1, 2. Be careful, remember H is with the X. There's the negative 1. K is with the Y. I've got to make sure I've got that. I need my A value, B value, C value for all my different pieces. I already said the transverse axis is the y-axis. Write that up there, but TA y-axis, or you can think of it as a vertical hyperbola. So in other words, I've got one going up, one going down. That's what I'm looking for. Okay. A would be 1. Square root of 1 is 1. B would be 2. Square root of 4 is 2. C would be 4 plus 1's 5. We add those bottoms, so that would be the square root of 5. So this means that my vertices are going to be 1 unit up and down from the center. Right. 1 unit up and down from the center, which would be -1, 3, and -1, 1. Now, I'm going to have to erase this to kind of make some space, but look at a graph at the same time. I'll leave this guy down here. So, one of the things that we can do, we can plot it as we're going along. So if I know the center's at -1, 2, so there's my center. Then I can count from here. I know I'm going up 1 unit. So there's 1 vertex. And down 1 unit. There's the other. Everybody know I've got 1 going down, 1 going up. So there's my vertices. Now, if I was asked for the foci, -1, 2 plus √5, -1, 2 minus √5. If I don't like the radical, I can certainly put in decimals for that. That's fine. Okay. The asymptotes. The important piece here, because it's going to tell me how wide to draw those parabolas. So the asymptotes. Y minus 2 equals plus or minus, and I know I've got an x plus 1 over here. So that's slope. If the transverse axis is the y-axis, if it's vertical, that means that slope is going to be the a over the b, which would be 1/2. It is okay to leave an asymptote in that form. If you want to distribute the half, you're going to have to write 2 equations. I would suggest either leaving it like this, or if you really wanted the y alone, leave this part and then just add the 2 on the outside, but either one would be fine. I needed that slope of a half, so I'm going off the center. So half slope would be up 1 over 2. Up 1 over 2. Notice I'm going right off the center. I'm going to make sure I have that center marked, and then I could draw my hyperbolas in. Something like that. All right, next up, we have been given a rational function before as far as f of x equals whatever, and then asked to find all the pieces, vertical, horizontal, oblique asymptote, x-intercept, y-intercept, what have you, and then graph the function. Now let's look at one going in reverse. Okay. If I'm going in reverse, I need to make sure I notice some key pieces here. Right. So here's my graph. I'm wanting to find the equation that this graph came from, or at least an equation this graph could have come from. All right. So let's get some important pieces here. Number 1, vertical asymptotes. I've got a vertical asymptote right here at -2, and I've got another one here at 2. Next important piece, horizontal asymptote. Right there at 1. Next one would be x-intercepts. I've got an x-intercept right here at -1, and I've got an x-intercept over there at 4. And last part, y-intercept here at 1. It's also where that horizontal asymptote was. All right, now let's see how we can build the equation from this. always like to look at my vertical asymptotes first. If we were going in reverse and finding all the pieces, then graphing it, we usually found the vertical asymptotes first. So I like to use those parts first to build it because I'm looking at the denominator because the vertical asymptotes were the domain restrictions. So since the vertical asymptotes are at -2 and 2, those would be the domain restrictions. So I would have an x plus 2, x minus 2 in that denominator. That would make the domain restrictions, make those vertical asymptotes at 2 and -2. Now it doesn't matter what order they're in, put the x minus 2 first or the x plus 2 first. X-intercepts come from the numerator. Well, anyway, I got an x-intercept at -1. So that would be x plus 1. I've got an x-intercept at 4. So that would be x minus 4. I would create those x-intercepts. Now we need to check two other pieces. We need to make sure horizontal asymptote is satisfied. Horizontal asymptote dealt with the exponents of the numerator and denominator. In this case, this would become an x squared. Actually, it would become a 1x squared up top. This would be a 1x squared on the bottom if it were multiplied out. Leading coefficients, 1 over 1 is 1. I can also make sure that my y-intercept is satisfied. Y-intercept would be if you substituted a 0 in for x. Well, if I substitute a 0 in for x, I would have -1 times -4 is -4 in the numerator. 2 times -2 is -4 in the denominator. -4 over -4, that's going to be a 1. I've satisfied all of those pieces. There is my answer. Now, let's say, I'll make a little change here. What if, I'm not going to change all the asymptotes and stuff, but what if I made this graph come up and cross at 2? So I'll make that guy a 2. Now if I look at it, vertical satisfied, horizontal or x-intercept satisfied still, horizontal satisfied at 1, but I'm not getting that y-intercept sitting at 2. So that's where we'd have to make some changes there. All right. What you're going to see, I will tell you, is it's going to go right through there. So it should make it a lot easier to work with. Last one we want to take a look at here would be a partial fraction decomp. And I want to look at this one because it's got this x squared here. And a lot of times we think, well, when we see that x squared and it's not factored out, can it be factored? This isn't an x squared minus 9 or something like that. I can factor, it's just an x squared. So it's not an irreducible quadratic, it's a repeater. Okay, there's really two x's there. So our split would have something over x, something over x squared, something over x minus 2. And that's where we'd have our A, our B, our C. Okay? It's a repeating piece, so we're counting up to it. You can kind of think of this as x minus 0 squared, more in that binomial format. That would work. Okay? So, common denominator, still going to be x squared, x minus 2. Building the numerator, we need to make sure it's a times what's down here in the common that wasn't in the original. Well, I got another x and the x minus 2. B times x minus 2. I had an x squared. This one's got the x minus 2. So c times just the x squared. So our original fraction, with our a, b, and c, what we know now is that at this numerator, x plus 1, has to equal ax times x minus 2 plus b times x minus 2 plus c times x squared. It has to equal that numerator. And then this is where we use values of x to help determine. Let's say x equals 0. I'm using 0. I like to use my domain restrictions. I got a domain restriction of 0 and 2. You can look at it here. You can look in this part. So x is 0, I'd have 1 equals 0 would take out the a term. It would take out the c term, because c times 0 squared. And it would give me negative 2b. B would be negative half. There's one of them. X equals 2. That would be a 3. 2 plus 1 is 3. 2 would take out the a term, because that makes that 0. Take out the b term. And 2 squared is 4, so I've got 4c. C is 3/4. Then for the next one, I don't have any other domain restrictions. This is where we just had to select an x value that we wanted to work with. You can select anything you want. You can select, well, I say anything. We don't want to select, we can't select 0 and 2. We've already used them. But anything else that you would like would work. For me, I would take a 3. I would probably either do a 3 or a 1. I want to stay small. The reason I'm selecting 3, I see 3 minus 2 is 1. If I chose 1, 1 minus 2 is negative 1, and I know I tend to mess up on some negatives there, but you can use whatever value you want. Right? So if x is 3, I'd have 4 on the left side. 3 plus 1. Over here, this 3 minus 2 is 1. Times 3 is 3a. 3 minus 2 is 1, so plus b. And 3 squared is 9, so 9c. It looks like I'm in a little bit of trouble, but I do know b and c already. So I can sub those in. So I would have 4 equals 3a minus 1/2. That was b. And then c is 3/4, so 9 times 3/4 is 27/4. I got a little bit of a mess here because of fractions. Remember though, if you're not the best of the fractions, you've got your scientific calculator can help you. Let's see if we can get these pieces together. Okay, I'm just going to move right up here. So that 4 equals 3a. Yeah, 3a. If I got a common denominator here, that would be negative 2/4 plus 27/4, which would be 3a plus 25/4. And actually, I'm going to go ahead and change this 4 to 16/4, just so I have that same denominator, because I'm going to have to bring that 25/4 over. So that would be 16/4 minus 25/4 would be negative 9/4. And then if I divide by 3, negative 3/4, there's the a value. And then we need to remember, we need to write it back into our original piece here. So negative 3/4 over x plus negative 1/2 over x squared plus 3/4 over x minus 2 in that format.